Now we're going to take a look at problem number 4 from the step input worksheet. And in this problem, we have a combination of two RL circuits together. We have R1 and L1 in series, and then that is connected to a parallel combination of R2 and L2. The switch has been open for a long period of time, and then suddenly the switch is closed, and we're interested in determining how the current through this inductor L2 will change as a function of time. So the first thing that we need to do is we need to derive a differential equation that's going to describe how this system behaves and how we can model the current through inductor L2 after the switch closes. So this is the system after the switch closes, and we have two distinct energy storage elements, L1 and L2, that can't be combined in series or parallel because of this resistor that intervenes. Therefore, this is going to be a second order system because of the two distinct energy storage elements. Now, we have a couple of approaches that we could use. We could use the node voltage method or the mesh current method. In the node voltage method, we have 1, 2, 3, 4 nodes that we would need to analyze, but one of them would be connected to our reference node. Therefore, we would need to couple two equations together. We could also use the mesh current method, which is the method that I'm going to choose. But again, we have two meshes, and these two meshes we are going to need to combine or couple together. So there's no way around doing some coupling in this example. So I'm going to call this mesh current right here I1, and I'm going to call this the IL2 current. Okay, so the first thing I need to do is to develop the mesh current relationship for I1. Okay, and remember that the mesh current method is based off of Kirchhoff's voltage law. So around this loop, we know that the potential dropped across resistor R1 plus the potential across inductor 1 plus the potential across resistor 2 must be equal to the potential that's applied by the supply V1. And again, we're going to make sure that it's clear that this is a unit step function because it occurs right after time is equal to 0. So now I'm going to use my current to voltage relationships and substitute in my I1 times R gives me the voltage across R1. The relationship for the voltage and current through an inductor is L1 times the rate of change of current through that inductor, and the current through that inductor is our I1 mesh. And the potential developed across resistor R2 is how the two meshes are coupled to each other. So we're going to have I1, and I'm based on my assumed directions, I'm assuming L2 is going counter to that, so I will subtract that. So this will be R2 times I1 minus IL2. And that needs to sum to be equal to V1 times the unit step function. Okay. Now I need to develop an equation for mesh 2. Mesh 2 again is based off of Kirchhoff's voltage law, and we have no supply in this mesh, so we're going to have the voltage developed across resistor R2 plus the potential that's developed across the inductor L2 must sum to 0. All right. The potential developed across resistor R2 is going to be R2 times IL2, the current in this mesh, and minus the mesh current I1 because they're going in opposite directions to each other. IL2 is going up and IL1 is going down. All right, plus the current to voltage relationship for the inductor, which is L2 times the current, the mesh current here is the IL2 dt, and that has to sum to 0. Okay, so now I want a second order differential equation that is in terms of, all in terms of IL2 so that I can solve for the relationship for the current through inductor 2. So to do that, what I want to do is I want to solve one of these equations so that I can substitute it in and get the second order differential equation all in terms of the current through inductor L2. All right, and the easiest way I see to do that is to solve the second mesh equation here for I1. Okay, and in doing so, I will get, let's see, I1 will be equal to, doing a little bit of algebra here, let's see, L2 over R2 times the rate of change of current through inductor L2 plus R2L times the current through inductor L2. Oh, sorry, I divided by R here, so that doesn't need, that term goes away. It's just the current through the inductor L2. Okay, yeah, so with that algebra intact, now I'm going to take this relationship and substitute it back into this equation for any time that I see I1. All right, and then this gets pretty messy here. So substituting into I1 right here, I will have R1 L2 over R2 times the rate of change of current through L2 with respect to time plus R1 times IL2. So that completes that first term. All right, I need to take the derivative of this and substitute it into here. So the derivative of this will give me a second order derivative and a first order derivative term, and I have to multiply those by L1. So this will be L1 L2 over R2 times the second derivative of the current through L2 with respect to time plus L1 times the first derivative of current through inductor L2 with respect to time. All right, so that takes care of that term. All right, next I'm going to substitute in right here. So I will have R2 times this. So that will give me L2, because the R2s will cancel, dIL2 dt plus R2 times the current through inductor L2 minus, I'll distribute this R2, so R2 times the current through inductor L2 is equal to V1 times the unit step function. Whew, okay. We see immediately that these terms go away, and what I can do is now regroup my terms. So I have my second order derivative here, which is L1 L2 over R2 times the second derivative of current through inductor 2 with respect to time. All right, and I have 1, so that was my second order. My first order derivatives are all right here. So I can add those up. It will be R1 L2 over R2 plus L1 plus L2 times the first derivative of current through inductor 2 with respect to time. And then my zeroth order derivative right here is R1 times IL2 is equal to the input voltage times the unit step function. Okay, to make things look a little neater here, this is not necessary, but just to make them look a little neater, I'm going to multiply everything by R2 so that I can get rid of coefficients that have fractions in them. So that will give me L1 L2 times the second derivative of current through L2 with respect to time plus, multiplying through here gives me R1 L2 plus R2 L1 plus R2 L2 times the first derivative of current through inductor 2 with respect to time plus R1 R2 times the current through the inductor plus R2 times the input voltage times the unit step function. Okay, so now we see that this is a second order differential equation, excuse me, and these now become my constant terms, M, C, and K. All right, since this is a little more tricky here, and my forcing function here will be F is equal to R2 Vn. All right, which will give me my new forcing function, my F over K would be equal to Vn over R1. All right, now from that, I can go and determine what my damping ratio is for this system. So I will pull up my Excel spreadsheet here, And because these terms are somewhat complicated, I'm going to do it in intermediate steps. I'm first going to determine my inertia term, which is the product of inductor 1 and inductor 2. My damping term is equal to R1 times L2 plus R2 times L1 plus R2 times L2. All right, and my stiffness term is the product of the resistances, R1 times R2. Okay, from that I know that the damping ratio is given by the constant C divided by 2 times the square root of m times k. All right, and when I do that product, I get a damping ratio of 1.18 or 1.19, so I know that the system is overdamped. Because I know that the system is overdamped, I'm also going to try to get the natural frequency of the system to find my eigenvalues. So the natural frequency of the system is given by by the square root of k divided by m. Okay, so that's in radians per second. And from that, I can calculate my two eigenvalues for the overdamped system. My eigenvalues are the product of the damping ratio and the natural frequency, or the negative product, plus the natural frequency times the square root of the damping ratio squared minus 1. And that same thing wherein we subtract the radical term. Okay, so now I have my two eigenvalues. Now, in order to come up with my solution, what I need to do is I need to take a look at the general solution for an overdamped system, and I know that if I can find my initial conditions, that my solution will be given by this equation right here. Right, and I can calculate the unknown coefficients a and b if I know my initial conditions. So what I'm going to do is I'm going to now turn towards establishing what those initial conditions are going to be. Okay, so to establish the initial conditions, we're going to take a look at what the circuit looks like before the switch closes and after the switch closes. So before the switch changes position, we have a situation that looks like this. All right, and we have an open circuit. We have nothing being supplied, and therefore, since the inductors act like a wire, in this case, we have no current, no initial current through L2 at time 0 minus. Therefore, that tells us, since the current through an inductor can't change instantaneously, the instant after the switch closes, the current also has to be 0 amps. Okay, now the next thing that we have to look at is what is the derivative initial condition. All right, so the derivative initial condition is going to be determined based on what our voltage law balances tell us. Okay, so as soon as the switch closes, we have this happening. We have our supply that's being connected. Okay, and we're looking for how the current, or the rate of change of current through this inductor right here. All right, the relationship that tells us about the rate of change of current through the inductor is the inductance relationship. So that is given by VL2 at time 0 is going to be equal to L2 DIL2 dt at time 0. All right, but now we can use a little bit of logic here. All right, we've already said that the current through the inductors at time 0 has to be 0. So 0 amps passing through that inductor. If there's 0 amps passing through this inductor right here, how much current can reach this node? Well, we see that 0 current can reach that node. So if 0 current reaches that node, and we have 0 current moving through inductor L2 right here, that must mean there's no current moving through this resistor either. Alright, so if there's no current through that resistor, that means there's no potential across that resistor. If there's no potential across that resistor, we also know that the potential across L2 has to be 0. So therefore, we know that this must be true. Alright, so since there's no potential developed across that resistor, and since there's no current coming into that node, we must know that the rate of change of current for L2 at time 0 must also be equal to 0. So that gives us our two initial conditions, our initial condition and our derivative initial condition. And now we can plug those back in and use the relationships to determine how the system is going to change as a function of time, how the current through that inductor is going to change. So our initial conditions are both 0 amps and 0 amps per second. F over K is the value of Vn, which is 7 volts, divided by the value of resistor R1, which is 3 ohms. Oops. Let's do equals 7 divided by R1, which is 3 ohms. Okay. Alright, so that gives us our final condition of amps. Alright, and now I need to insert a couple of columns here so that I can, or excuse me, a couple of rows so that I can calculate my coefficients. The coefficient for the overdamped system is given by the coefficient B is given by the derivative initial condition plus the first eigenvalue times F over K minus the initial condition. All of that is divided by the difference between the second eigenvalue and the first eigenvalue. Alright, and A is given by the initial condition minus B minus F over K. Alright, so now that we have those values, we can now enter our general our general step input solution again, right here. We can put that equation into Excel and plot what that's going to look like as a function of time. Okay, so at time 0, oops, alright, I'm going to have, 0. At time 0, I'm going to have A times the exponential function raised to the lambda 1 times time plus B times the exponential function raised to the lambda 2 times time plus F over K. Alright, and then I'm going to step this in, let's see, we'll try steps of 0.1 first and see how that goes. Okay. And it looks like it looks like we should do a little bit finer resolution on our steps here. So let me go 0.05. And plot the results. Okay, so for this system we see that the current through the inductor L2 is going to start off at initially 0 current, 0 amps, and it has a rate of change initially of 0 as well, and then quickly it's going to shoot up in this overdamped case, and it's going to approach a value of 2.33 amps. All right, and that solution is also available in written form on our solutions worksheet here. So this is how we would express that in our written form. And you can see the eigenvalues and the values of the coefficients A and B, as well as the value of the F over K, which is the 7/3 there. Okay, so I think that is the solution, the final solution to all of our step input worksheet problems. I hope this has been beneficial for you to see how all of the solutions were derived.